Okay, so we need to cover two specialized topics in order to be able to do the homework. Um, One is the kinetic energy coefficient. So if we write out our Bernoulli's equation, which is P over rho plus V squared over 2 plus GZ out is equal to P over rho plus V squared over 2 plus GZ in plus W dot pump plus losses. Um, the important thing to remember about this is we had to assume uniform properties. And what uniform properties mean is that pressure, velocity, and height are uniform across the entrance and exit. This is actually pretty decent assumption for pressure and height a lot of times. But for velocity, there aren't many practical situations, practical examples where the velocity is actually uniform. If we're looking at a pipe under highly turbulent situations, the flow rate, the velocity profile can be nearly uniform. It kind of comes up, comes across, and then comes back down like this, and so it looks like a what's called slug flow because it looks like a slug that is used in bullets for a gun, or I don't really know. Anyway, it's called slug flow. It's nearly uniform, and in that case, using our average velocity v bar in our equation here works pretty well. However, in laminar flow, we'll draw it over here. Actually, we'll draw it later here. So in laminar flow, we know we have a parabolic flow. We solved for it in Navier-Stokes equation. And with a parabolic flow, the average velocity is not a good approximation of the total kinetic energy of the system. So what we have to do is we have to introduce a fudge factor, and that fudge factor is called the kinetic energy coefficient. And to solve for that fudge factor, basically, remember all this equation up here is divided by m dot. So we're going to multiply back through by m dot. So we're going to put m dot here, here, in front of both of our out and in sections. That changes our lowercase wp into a capital WP, and changes our losses into a capital losses. Really what it does is change the units on both of those. Capital W dot P is now in watts, and losses is now in watts. Then we can say, all right, so we have a m dot alpha v squared over 2, v bar squared over 2, where this is remember v bar is equal to the average velocity. That is going to be, we want to set it equal to the actual amount of kinetic energy that is crossing our boundary. So this is going to be equal to the integral of rho times v squared times w dot n hat dA. So let's take that down here. We can then solve for alpha. Alpha then becomes equal to the integral of rho v squared w dot n hat dA divided by m dot v bar squared over 2, where v bar is our average velocity. We've had to calculate it before, but I'll remind you guys how to do it here. V bar, our average velocity, is equal to the integral over our area of our velocity times velocity integrated over our area divided by our area. And remember, your m dot is equal to the integral of your rho times w dot n hat dA. So if our flow is perpendicular to our control surface, then m dot is equal to the integral of rho times velocity dA. And remember, if we have density is equal to a constant, then we can pull the density out, and m dot then is equal to rho times integral of v dA, which is equal to rho times v bar times a. Cool. So we know how to get m dot, we know how to get v bar when we have a variable velocity across our inlet and outlet. Now the only question is how to handle this upstairs quantity. Well, that is not as hard as we think. Again, if our flow is perpendicular to our control surface, then this integral up here on top becomes the, and we assume, so flow perpendicular to control surface and density is equal to a constant, then we can say alpha is equal to the integral, rho times the integral over our control surface of v squared times v dA divided by m dot v bar squared over 2. And this becomes then v cubed on top, which we can actually let's just erase that and make that v cubed. And then the only hard part about this is setting up this integral and setting up the average velocity integral and doing them. So remember, this setting up your differential area is tricky, but oftentimes, for example, if we have two infinite plates, and this is the x, y, and z direction, then the area you're integrating over is a differential area like this. It flows in this direction, where you have integrating in the y and then pretty much a unit vector in the z direction. So you could just say, in this case, dA is equal to 1 dy, because you have a unit vector in the z direction. Nothing's changing that direction. So when you integrate, it's not a function of z, so nothing happens, right? And then plug in your value for v, or in this case it would be u, because it's in the x direction, and integrate, and you're done. The other one is the other important thing to talk about is what's it called? The minor loss coefficient. So a minor loss coefficient is a way of, we're going to talk about this, but it's a way of modeling the losses that occur here. So we talked about losses, and we said we'd model those in a future section. Well, we're getting a little bit of a jump start here. And so we can say that our minor loss coefficient is defined as, so head loss minor, here's how I'll say it, is equal to k, which is our minor loss coefficient, times v squared over 2g, where this is v bar squared. So when you're solving for this coefficient, you need to you need to kind of rearrange some stuff in your equation. So in the flow that we have for example, the homework problem, you have just 0 is equal to, you have, for your stuff that's leaving, you only have a v bar squared over 2 out is equal to a v bar squared over 2 in plus 0 for the w dot plus your losses. Remember, if we divide by g, then this becomes head losses, and that's what we want to get there, because we're trying to get into a situation where we can approximate this equation. And so we know that our head losses are equal to v bar squared out over 2g minus v bar squared in over 2g. And we can rearrange this then to substitute in our what we know. Sorry, there's an alpha here. We have to put that alpha in. Gosh. Alpha and an alpha here. So we can substitute in this. We know this as well. We know this and we know this. We can substitute it in and then pull out the stuff that matters in front of a v squared over 2g. And this is our minor loss coefficient.